Good morning, and welcome again to this lecture of electronics in which we were studying communication. I guess we have completed all sorts of modulation techniques that are in our syllabus, and today we are going to continue the sum of the derivation portion of frequency modulation. Right. So let us begin with that. Uh, yeah. To start with, let me introduce myself. Myself, Dr. N.D. Mishram. Yeah. So I guess my screen is visible to you. Myself, Dr. N.D. Mishram, Head and Associate Professor, Department of Electronics, Sri Mathura Das Mota College of Science. And now today we are going to study more about the derivation portion of the frequency modulation, right? So I guess you know what is frequency modulation by now because we have, I guess, revised it many times. So let us briefly understand again what is frequency modulation, right? So frequency modulation in it comes under the angle modulation techniques. So angle modulations are of two types. The one is the frequency modulation, and the other one is the phase modulation. Right. So we are having two types of angle modulation. Initially, we were having amplitude modulation. Right. So we have studied in depth what is amplitude modulation and the derivation portion of it. Now, in this portion, we are going to study about frequency modulation. So it comes under the head of angular modulation, and angle modulation is are of two types: frequency modulation and phase modulation. Right, so we'll be considering this frequency modulation today. Okay, so what is frequency modulation? The frequency modulation is a technique of modulation in which the frequency of the carrier is varied in accordance with the amplitude of the modulating signal. Again, I'm repeating it for you. The frequency modulation is a technique of modulation in which the frequency of carrier is varied in accordance with the amplitude modulating signal, right? Keeping the phase and the amplitude are constant, right? So keeping phase and amplitude as constant. So these are the basic definitions. In amplitude modulation, we have learned that the amplitude of the carrier wave is being varied in accordance with the amplitude of the modulating signal, keeping phase and frequency as constant. Right. The same definition is repeated over here, just some change of words. Over. Okay. The information is conveyed via frequency changes. Right. So this is the main job of frequency modulation. We have already studied this, and these are the waveforms, right? So the upper wave, the topmost wave is a modulating signal, which is shown over here, and this is the carrier wave, which is having a higher frequency. And when we superimpose it or when we mix it, we get this type of the change in the frequency, right? So here it is having the same frequency nearly. Now here, since the voltage, the amplitude of this modulating signal is being decreased, so it will have a change in frequency, which is shown over here, right? So this portion is showing you the minimum frequency, and this portion is showing you the maximum frequency. So there is the change in the frequency of the carrier with respect to the amplitude of this modulating signal. That is called as the frequency modulation. So we have studied this earlier also. Okay, so let us start with some of the derivation portion of this modulation index. The first one is the definition is modulation index is defined as the ratio of the frequency deviation that is dealt to the modulating frequency, right? So we have also defined the same in the amplitude modulation. So we were having modulation index in amplitude modulation too. Now in this case, in frequency modulation, what is the definition of the modulation index? The modulation index is defined as the ratio of frequency deviation that is dealt to the modulating frequency Fm. Okay, so this is the definition, and if you write it in formula, so it looks like this. So frequency deviation by modulating frequency, that is nothing but del upon Fm, right? So modulation index of frequency modulation equal to del by Fm, and if the frequency modulation, that is modulation index of frequency modulation, is greater than 1, then the modulation index of Fm decides the bandwidth of Fm wave, number of sidebands that are supposed to appear in the wave. So these are some of the results that we can actually see in the waveform. Right? So I will be showing you the waveforms and what happens with the sidebands in frequency wave, frequency modulation, right? Okay, so this is the definition of modulation index, and then deviation, that is the deviation ratio. The modulation index corresponding to maximum deviation and maximum modulating frequency is called the deviation ratio, right? So the modulation index, now we are having MI corresponding to the maximum deviation, that is del, and to the maximum modulating frequency, that is called as deviation ratio. And the formula can be written as deviation ratio is equal to maximum deviation divided by the maximum modulating frequency. So we are having the maximum frequency I've shown in the waveform itself, and maximum deviation, how much deviation we have with the original one, right? So that is given by again del max by f max. In FM, that is frequency modulation broadcasting, the maximum value of deviation is limited to 75 kilohertz, whereas the maximum modulating frequency is also limited to 15 kilohertz. So it won't have variation beyond 15 kilohertz, I guess. Okay, so this is for the frequency modulation and the deviation ratio. The next one is the percentage of modulation index of frequency in frequency modulation. So that is, I guess, if you multiply it by 100, then it becomes the percentage modulation. The percentage modulation is defined as the ratio of the actual frequency deviation produced by the modulating signal to the maximum allowable frequency deviation. So that is the percentage, and if you need to write it in formula, so percentage deviation will be modulation index is equal to actual deviation divided by the maximum allowable deviation, that is shown over here, right? So yeah, so this is the formula of percentage multiplied by 100. So that will give you the maximum modulation, percentage modulation index. Again, I am repeating the definition for you. The percentage modulation is defined as the ratio of the actual, sorry, the ratio of actual frequency deviation produced by the modulating signal to the maximum allowable frequency deviation, right? So that is the percentage deviation. Then the next one is the mathematical representation of FM. Now, how FM will appear, frequency modulation waveforms, what would be the actual derivation portion of it? So that is being shown in this. So modulating signal is like this. Then it may be represented as, now this sine wave, which is the modulating signal, can be represented as we have studied this in, say, amplitude modulation, it is represented as EM equal to EM cos omega m into T. So this is the this M stands for, say, the modulating signal. So this is the amplitude, and this is the maximum amplitude EM over here, capital EM, right? So this is a small EM which gives the exact location according to omega t, and this EM is supposed to be the amplitude, the maximum amplitude as shown over here, maximum amplitude of the modulating wave. Okay, modulating signal. And this is the omega mt, that is change uh, cos of omega m into t. Okay, so let us start. So here cos term taken for simplicity, and em is the instantaneous amplitude, omega m is the angular velocity, that is equal to 2 pi fm, and fm is the modulating frequency. So these are the terms which are being taken for consideration. So where we have considered this, so em is equal to instantaneous amplitude, that is the exact amplitude at time omega mt, and omega m is the angular velocity, that is equal to, that the formula of that is given by 2 pi fm, that is the frequency of modulating frequency fm is. So this is the expression for this sine wave. Then for the carrier signal, again the carrier signal looks like this. So for carrier signal, we are taking it like say EC as the maximum amplitude, and omega CT as the, say, phase angle. So we are having this EC equal to capital EC. Capital EC is taken as the maximum amplitude, which is shown over here, and sine of omega CT plus phi. Phi is again the phase angle that is associated with this carrier wave, where EC is instantaneous amplitude, that is any of the point which is in the wave, and then omega c is the angular velocity, then which is given by 2 pi fc, and fc is the carrier frequency. So these are the expressions for this carrier wave. This is same as we have taken it for the modulating signal, just a difference that we are using it for carrier, and there we are using it for the modulating frequency. Okay, so these are the equations. Now, phi is the phase angle. Yes. So we are keeping phase as constant and amplitude is still as constant. So FM wave can be taken as, so this is the del, that is plus f to minus f, that is frequency versus time we have taken. So FM is nothing but deviation of frequency from figure to figure this. Instantaneous frequency f of the FM wave is given by f equal to fc into 1 plus k em cos omega mt. So this is the instantaneous frequency which we are expecting to as an output of say the frequency modulator circuit. So f will be equal to f will be equal to fc into 1 plus k em cos omega mt. So this is the equation of say the modulating frequency em, small em, and these are the constants. So fc is the frequency of the carrier, right? So again, fc is the unmodulated carrier frequency. Then k is the proportionality constant. Em cos omega mt. We have already seen this. This is equal to small em. That is instantaneous modulating signal. And this cosine term preferred for simplicity. Otherwise, we can use sine term also. So we can use both of them. Here it has been used as sine. Okay. So this is for the FM wave, and when we uh, say when we try to solve it, the maximum the maximum deviation del will be given as will be given by del equal to KEM FC, and the instantaneous amplitude of FM signal is given by this EFM is equal to A sine F omega C omega M, right? So this is the frequency modulated signal, and if you substitute, then we will be having A sine theta. We have substituted this as theta over here. Again, some function of carrier and modulating frequency, that is function of omega C and omega M. Let us write equation 2.26 in terms of omega as omega is equal to omega C 1 plus k E m cos of omega mt. Now instead of f, we are taking it as omega. So omega is equal to 2 pi fc. So we can write like this. So omega is equal to omega c 1 plus k E m cos omega mt. The to find theta, omega must be integrated with respect to time. So if you integrate it, we have theta is equal to omega into dt. Taking integration, so theta will be equal to omega c 1 plus k em cos omega mt into dt. Similarly, omega c, by resolving it, we can have say omega c 1 plus k em cos omega m into dt. Okay, so this can again be written as cos omega t can be written as sine of omega mt by omega m, that is km. Okay, so it comes out to be, if you take it as common, we'll having omega c t plus k e m omega c sine omega mt by omega m. Okay, so this is the derivation portion. Yeah, so if we again resolve it, we can have omega c t plus KEMFC. I guess we are having the same, sorry, we have replaced this omega c by fc over. So KEMFC to sine omega m by omega t. Okay, so now further resolving it, we are having omega ct plus del sine omega mt, since del is equal to KEMFC. So del is the maximum deviation that we have. Since then substitute value of theta in equation 7. Thus, we get EFM is equal to A sine omega ct plus del sine omega mt divided by FM. Then again, solving it, we'll be having A sine omega ct plus FM, MF sine omega mt. This is this equation number 9 is actually the equation of the frequency modulation. So that whatever we have seen over here, according to the change in the amplitude, we'll be having this type of a say equation or waveform. And the second one is the frequency spectrum of FM. So frequency spectrum of FM is a graph which is say derived from the amplitude versus the frequency. Again, the frequency spectrum of FM wave tells us about number of sidebands present in the frequency modulated wave and their amplitude. Okay, so this is the frequency spectrum, and this expression for FM wave is not simple. It is a complex because it is a sign of sine function. Only solution is to use Bessel's function. I guess we don't have this much of there in our syllabus. So we can skip that. Maybe we are concerned with the last equation that we derive. So from this equation, it is seen that the FM wave consists of the first one, that is the carrier, first term in equation, infinite number of sidebands, all terms except first term and or are sideband. So first term रहेगी वो छोड़कर बाकी सब sideband. I will show you the graph actually. The amplitudes of the carrier and sidebands depends on J coefficient. So whatever equation we have derived from over there. So omega C is equal to 2 pi fc and omega m is equal to 2 pi f. So in place of omega C and omega m, we can use fc and fm also. So just we can replace this by 2 pi fc or say in that case omega. So we can have different equations. That is what I was talking about. So this is the frequency spectrum of frequency modulated wave. And here you are able to see the first one, that is the carrier frequency, which is at the center. And then we are having the side bands. So we are having FC minus FM, then FC plus FM, right? Similarly, we are having FC plus twice of FM, FC plus thrice of FM, and four times FM. Similarly, so there are n number of side bands, infinite number of sidebands in frequency modulation. Similarly, on the negative side, we are having the subtraction of that. So Fc minus 5 FM, Fc minus 4 FM, so and so on, so on and so forth. Right. So this is the frequency spectrum of a frequency modulation. I guess we are you having any questions on this? This is actually the changing amplitude. So amplitude is highest at the carrier frequency and it goes on decreasing for the sidebands, respective sidebands. Okay. So that is shown over here. Perfect. So anybody is having any problem, you can ask. Okay. So this was for the sideband. Now, what effect we are having of the modulation index, say the bandwidth. Okay. So first we'll see the bandwidth, then we'll see the what is the effect of modulation index on say the sidebands. Okay. So let us see this. So from frequency spectrum of FM wave shown in figure 2.26, we can say that the bandwidth of FM wave is infinite. As I've shown you this diagram. Yeah. So this diagram shows you that they are having infinite sidebands over there. Okay. Right. But practically, it is calculated based on how many sidebands have significantly amplitude. So the rest of the sidebands are having lower amplitude, which are say now not noticed by the receiver section. So we are concerned only with which are having prominent amplitudes, right? So the rest of are being say avoided or neglected. Now, by simple method to calculate the bandwidth is nothing but twice of FMX, number of significant bands, right? So with increase in modulation index, the number of significant sidebands increases, so that bandwidth also increases. So we can have a bandwidth. The second method to calculate the bandwidth is by the Carson's rule. Carson's rule, still we are not concerned about this. They are in very depth. So we won't go in depth over there. So this is what I need to show you, that the effect of modulation index on sidebands. So if we are having a modulation index of 0.5, 1, 2, 2.5 and 4, then how the sidebands will appear. That is what I was expecting to show you. Right? So this is the different waveforms for different say modulation index. So for zero point 0.5 modulation index, we are having these two sidebands, right, on either side. So the on plus side also FC plus FM and FC plus twice of FM. Similarly, FC minus FM or FC minus twice of FM. Now remember, these are prominent amplitudes, right? So we are having n number of say infinite number of sidebands, but these are the prominent ones which amplitude can be noticed. Okay, so that is why they are considered over here. So 0.5, say for modulation index 0.5, we are having two sidebands. Similarly, when modulation index is 1, then we'll be having three sidebands, means on either side. So on both the sides, we will be having these. So we are having 3 plus 3, that is 6. Okay, so we call it as our sidebands and the lower sidebands. On negative side, we'll be calling it as a lower sideband, where in the positive side, we'll be calling it as the upper side. So for modulation index 1, will be having three sidebands. Similarly, for modulation index 2, we'll be having four sidebands. and 2.5 will be having 5, or 4 will be having 7. Sorry. So this is how it changes, right? So we are having different side bounds for different, say, modulation index. This is what I need to show you. I just, you have understood what are the significant side bands. So I guess up till now, this will be okay for today. And if you have any issues on that, we can just revise it. So yeah, let us start from this beginning. So today we are going to consider some of the derivation portion of, say, the frequency modulation, right? So in that case, what we have seen is we are having angle modulation, two types of angle modulation. The first one is the frequency modulation, and the other one is the phase modulation. Then we are concerned with frequency modulation. So frequency modulation, the definition of frequency modulation is there, and this information is conveyed through the frequency. We are changing the instantaneous amplitude of the modulating signal with the change in frequency with the amplitude of the modulator, right? So there is change in frequency. So here it is having a maximum frequency, and here it is having a minimum frequency. So for the derivation portion of it, modulation index is equal to frequency deviation by modulating frequency del by FM. And I've shown this in FM, if modulation index is greater than 1, then modulation index of FM decides bandwidth of FM wave, number of sidebands in the FM wave. So these are some of the points which are dependent on, say, the modulation index. Deviation ratio, the modulation index corresponding to deviation and maximum modulating frequency, right? So the ratio of maximum deviation to the maximum modulating frequency is called as deviation ratio. That is, the formula is like this. So deviation ratio is equal to del max by f max, right? So the maximum values are 75 kilohertz and, say, the 15 kilohertz accordingly. The next one is the percentage modulation index of FM. The percentage modulation is defined as the ratio of the actual frequency deviation produced by the modulating signal to the maximum allowable deviation, right? So the percentage modulation index is equal to actual deviation divided by maximum allowable deviation. Okay. So maximum mathematical representation of FM gives us modulating signal. Modulating signal looks like, the equation is Em equal to Em cos omega t. These are the considerations, the nomenclature that we have taken. Em is equal to instantaneous amplitude. Omega m is the angular velocity, that is equal to 2 pi fm, and fm is equal to modulating frequency. Similarly, we are having for the carrier wave, EC equal to EC sine omega ct plus pi, where EC is the instantaneous amplitude, omega c is the angular velocity, and is equal to 2 pi fc. Fc is the carrier frequency, phi is the phase angle. Right? So we are going to keep phase angle and amplitude as constant. So FM is nothing but deviation of frequency, and that is the formula can be given as the frequency modulation is Fc equal to 1 plus k Em cos omega mt, and where Fc is equal to unmodulated carrier frequency, k is the proportionality constant, Em cos omega mt is the modulating instantaneous modulating signal, right? So this is the formula for frequency modulation, and cosine is preferred for, say, for this simplicity. So that maximum deviation del will be given by del is equal to k EMFC. Instantaneous amplitude of FM signal is given by EFM a sine omega, sorry, function of omega c and omega t. That we can write as a sine omega t, a sine theta. And if you substitute in terms of, say, omega, we'll be having omega equal to omega c 1 plus k em cos omega t. Similarly, can be integrated to get the to find theta angle angular displacement. So we can say define integrate this, theta is equal to omega dt by equal to omega c 1 plus kem cos omega m into dt. Theta is equal to omega c 1 plus kem omega mt dt. And yeah, so this is how we can derive this. Yeah, here is the last one. So omega ct plus kem fc sin omega mt by omega m. This is the equation of the angular displacement. Okay, so substituting the values of this in this equation, we can have EFM is equal to A sin omega ct plus del sin omega mt by FM. right? So we are having the whole of divided by this. Then yes, again solving it and substituting the values as this of frequency, we can have EFM A sin omega CT plus MF sin omega M into T. These are in suffix. Okay, so this is the equation of frequency modulation, and this is for the frequency spectrum. So we can have this. We are having a number of sidebands. I guess we have infinite sidebands in frequency modulation like this. So these are some of the terms, and these are the sidebands which are there, and it is according to the amplitude to the frequency. So the prominent amplitude having sidebands will be considered, and rest of the amplitudes are being say avoided or neglected. Okay, so these are the modulation index. Yeah, price of FMX, and these are the effects of modulation index on say the sideband, which I have shown over. So I guess this much is enough for today. Thank you very much for joining. And if you have any queries, I'll be happy to resolve it. So do you have any queries? You can ask me on that. Right. So thank you very much for joining. And we'll be meeting you in the another class. So stay tuned to my YouTube channel. I will be uploading this video and the other more some more videos on communication on my YouTube channel. Please go through it, like, share, and subscribe my channel. Thank you very much. Stay home, stay safe, take care. Please take precaution of yours. Good day.